Assalamu alaikum. Welcome to my presentation on leveraging a bank transaction dataset for fraud detection. This project emphasizes the role of statistical analysis and machine learning in identifying fraudulent patterns in transaction data. Today, I will walk you through the dataset, the key statistical insights derived, and how these insights inform the fraud detection process. Introduction to financial fraud detection. Financial fraud is a growing problem costing billions of dollars annually. The challenge lies in detecting fraud amidst millions of transactions where fraudulent events are rare, making this a statistical needle in a haystack problem. Machine learning, when combined with statistical techniques, allows us to identify patterns in historical data to improve fraud detection rates and reduce false positives. Here we will understand that dataset structure. The dataset includes essential attributes like transaction ID, amount, time, merchant category, location, and a binary variable indicating where the transaction is fraudulent. From a statistical perspective, each variable offers opportunities for descriptive analysis. For instance, transaction amounts allows us to explore measures of central tendency like mean and median, while location data can reveal distributional anomalies. This structured approach to the dataset provides the basis for further statistical modeling. Exploratory data analysis or EDA is a cornerstone of statistical investigation. First, we visualize transaction amounts to identify outliers using box plots and histograms. These outliers are often linked to fraud. Next, we analyze the time of day using density plots to identify peaks in fraudulent activity. Lastly, we use bar charts to examine merchant categories, calculating fraud rates within each category to identify high-risk sectors such as luxury goods. Identifying suspicious transactions, statistical thresholds help flag suspicious activities. Transactions occurring in unusual locations can be detected using z-scores to measure deviation from expected behavior. Large transactions amounts are flagged when they exceed a statistically significant threshold, such as 3 standard deviations from the mean. Similarly, we identify uncommon times of the day by analyzing time series patterns and checking for anomalies against historical trends. This slide feature engineering for fraud patterns. Feature engineering involves applying statistical transformations to create meaningful inputs for our model. For instance, transaction velocity measures the frequency of transactions per time period, analyzed using moving averages. Spending deviation is calculated as the difference from a customer's historical mean, a classic application of variance. Merchant history flags merchants with higher fraud rates, derived from prior frequency tables. These features enhance the predictive power of our model. Here are the techniques for selecting appropriate machine learning models. Machine learning leverages statistics at its core. Logistic regression, for example, uses statistical likelihood to model binary outcome like fraud detection. Random forests use bootstrap sampling, a statistical technique, to build robust ensemble models. Support vector machines rely on geometric separation, but their performance hinges on statistical measures like kernel functions. Each model brings unique statistical strengths to this classification task. In this slide, we will discuss training and evaluating the fraud detection model. Statistical rigor ensures reliable model evaluation. We split the data into training and testing sets, typically using an 80-20 split to prevent overfitting. Performance is evaluated using metrics like precision and recall, calculated from a confusion matrix. These metrics help quantify the trade-offs between catching fraudulent transactions and avoiding false alarms, both critical for operational use. Here we will discuss about deploying the fraud detection system. Once trained, the model is integrated into the bank's transaction system. Real-time monitoring relies on statistical process control to track model performance over time. Feedback loops allows us to adjust statistical thresholds and retrain models with new data, ensuring the system adapts to emerging fraud patterns. Last, we will conclude and also discuss the next steps. This project demonstrates the power of statistical analysis in fraud detection by identifying anomalies, measuring deviations, and leveraging predictive models. We can significantly reduce fraudulent activity. Moving forward, regular updates to the dataset and advanced statistical techniques, such as time series analysis or Bayesian inference, can further enhance model accuracy and robustness. Thank you.